welcome to That's Absurd. Please elaborate. I am one of the half of the hosts, Trace Dominguez.
and I'm the other one of the half of the hosts, Julian. That makes it sound like we're stitched together or something.
Hey, we've done videos like that. It's happened.
We have. The teleporter malfunctioned. I remembered that one.
It was a really good
times.
Video. I like that one
Good times. Those were the days. This is That's Absurd. Please elaborate. The show where we take all sorts of silly, wacky, weird questions from each other, listeners, guests, and then we try and apply our researching science communication skills to actually finding a viable answer, if you could believe it.
Sometimes the answers aren't that viable.
No.
But we do.
Look, it's all
best.
Made up and the points don't matter anyway.
That's
but
right.
It is fun. Can't things just be fun?
Yeah. If you want to submit a question for us to answer, you can look in the show notes for a link, or you can go to our website, that'sabsurdshow.com/ask to submit a question. You can also send it to us any number of other ways. We're on social medias and stuff like that. But anyway, we get our questions from listeners, from each other, and even from our friends and family. So please submit them, because that's how we keep the show going.
Pin a threatening note to our door with a knife. And then you open it and it's like, what if kittens were puppies or something?
What if kittens were puppies?
I don't know. I'll have to look into that.
We'll have to look into the science. So this week we've got 2 questions from 2 different listeners. But first, I think we're going to go with Julian. Julian, what is your question?
I am so excited about this one because it was a total rabbit hole to follow. This is the question. The listener asked to remain anonymous, but they said, if I had some magic communicator to speak to someone in another galaxy, could I explain what left and right were?
Whoa.
And I love it because it sounds so simple, doesn't it?
You're just like, oh, left and right.
Left and come on,
Oh,
you
man.
know what left and right is. And this listener elaborated further. I'd want to explain what left and right were to someone so that if we ever met, they would agree. The hardest case is someone in another galaxy with a magic communicator. I've thought about this for a while and once asked a physicist friend. I heard it somehow relates to CPT symmetry. I don't understand the T of that part, but that's probably not the most interesting thing to discuss on the show. And I like how they already kind of started doing the research for me. They're like, what's this? By the way, I've asked a physicist. And you're like, wow, you did some legwork.
I mean, that's more than what we do sometimes.
But it's such a great question, I think, because it does sound so deceptively simple, right? Like, Trace, how would you define left?
I mean, it's the left is left. It's to my left.
Go on.
Julian.
I know.
Oh, no.
I know.
It's the left is the one where your finger and your thumb make an L.
Okay, what if I have no concept of the alphabet as we know it? Then what?
No.
Oh, no,
left
right?
Also,
oh, no. If I hold up my hands right and you're looking on the other side, which of my hands makes the L?
It's the wrong one.
It's the wrong one.
Oh, no. Okay, so if I have, oh gosh, there's got to be some universal way to do this.
Do not feel so bad about it because I went to dictionaries, just to see, because I started thinking and racking my brain. If I had to describe left to somebody who had no concept of it, where would I even begin? And it turns out, like, dictionary definitions that I found for this are terrible.
Oh no, give me one. What do they say?
Yes, okay. Webster's defines left as, quote, of relating to, situated on, or being the side of the body in which the heart is mostly located.
What? What if I'm not human?
There's that. What if I have X-ray vision or any knowledge of anatomy? How am I going to know where the heart is mostly located? And by the way, it's pretty much in the center. Just your left side of your heart is stronger because it has to pump blood through all of your body, where the right side just pumps it through the lungs. That's why you feel your heartbeat more on the left.
Yeah.
But the whole, being American, doing the Pledge of Allegiance, and your second grade teacher's like, you put your right hand over your left side of your chest because that's where your heart is. No. It's just your left side is stronger. Anyway, so I thought that sucked. And like you said, what if you're an alien and your heart is somewhere else? What if, here's the thing, your alien body plan isn't bilaterally symmetrical like a human's is.
Yeah, that's
right?
something I thought about when you were like, how do you define left? And my first thought was, if I'm defining it for something that's an alien, I can't assume bilateral symmetry because they may not have evolved from the same thing that we did.
Exactly.
I mean, the assumption is that that's the simplest way to evolve, but that's just because we don't know. We're just like, oh, well, this is the simplest. But we don't know that.
Yes, exactly, right? Like, we see, mostly on Earth, we see things either with bilateral symmetry, right? Where you could, like, drop a plane down the middle of it, and, like, on either side of it,
like it's 737. Drop it right down the middle.
I knew you were going to say that. Yeah, just drop a plane on a lobster, and it's symmetrically squished. No, but like, slice it right down the middle, and the left side basically looks like the right side, right? Oh, crap, now I'm using left and right in the definition. But you know what I mean. And then there's radial symmetry, right? Like a sea anemone or something where just like, it's a circle, right? You could put the plane in all sorts of orientations and still get that symmetry. And then there are things with neither of those, right? Just like a sponge or coral, it doesn't really have like, it's an animal, but it doesn't have a symmetry in any of those dimensions, right? So I don't even know where to begin defining left and right with those. And this Webster's definition also assumes one heart. What if you have more? What if you have fewer? I don't know. That's not great. So Webster also has more definitions, and they just get worse, right? Webster's also defined left as done with the left hand. Located nearer to the left hand than the right. Located on the left when facing downstream. That's when we're talking about the left or right bank of a river. That confuses people sometimes because they're like, what do you mean left bank? And it's like, okay, when we're talking rivers, you face downstream and then it's left and right. Or located on the left of an observer facing in the same direction as the object specified. Which again, we're assuming a face. Right? We're assuming that something that what we're talking to can face a direction.
You know what this reminds me of is the thing where they're like, okay, we have nuclear material and we need people 10,000 years from now to understand that this is dangerous. We don't need to tell them what it is. We just need them to know they shouldn't go near it and they shouldn't pick it up and carry it around. How do you do that?
Right.
And this is like another way to think about that same problem, which is like, there is no inherent meaning to anything, and to find it is absolutely maddening.
Yeah. I mean, it's an added layer of complexity because we're assuming that what we're telling, 10,000 years in the future, that this stuff is radioactive and dangerous. We're assuming that's still talking to humans, right?
Yeah.
So we understand a bit about like human behavior and what humans react to and what humans freaking look like, right? And the stuff they come up with is generally just like the most nightmare fuel looking, like large, jagged stone pillars that like, and to further drive it home, there's been discussions of some sort of code that translates to like, what we keep here is not sacred, or like, what is here is disgusting to us, which I've seen, by the way, somebody took and printed on the butt of those little shorts that like, you usually just say like pink, and I would like a pair, just saying. My birthday's coming up. I think they'd be cute.
It says disgust.
Disgust. What we keep here is not sacred.
When we get a merch store.
Okay. So yeah, it's exactly what I'm thinking, and then add on the complexity of like, we don't even have a clue what we're talking to might look like, or like the conditions of the planet that it's on. And so that brings me to like Oxford's definition, which I thought was a little closer to being useful. And you might see why, right? They define left as on, toward, or relating to the side of the human body or of a thing that is to the west when the person or thing is facing north.
So yeah, that I get. I get why. Right. I like that better. We can't assume that, the planet that these aliens come from have that, but it is at least a planet, right?
Right.
It's at least a sphere-ish, oblate spheroid or something like that, where we can you can start to relate.
And we're putting these things in terms of stuff that's a bit more objective, right?
Yeah.
Like, I could tell that to other humans anywhere in the world, assuming they could understand the language, and they'd get what I'm saying. But exactly like you mentioned, we're making a lot of assumptions about the planet that these aliens we might be talking to are on, right? Mm-hmm. Like, and facing, again, we're talking about symmetry, but also like, how do we define north, you know?
Yeah.
That then it starts to get hard again for us to be like, oh, you see these stars above you, but for a planet in another galaxy, which is the specifics of the question,
Yeah.
they don't have
They may not
those
have that.
constellations to reference, right?
Wow. This is hard.
It's so hard. And then on top of that, right, like we could say, okay, north is one of the axes that like the planet rotates through, you know, where like longitude lines come together sort of thing. And that's, again, kind of tough. And then maybe we say, oh, west is where the sun sets. And now we're assuming that the planet rotates the same way.
Right.
Because Venus rotates the opposite way. So that instruction on Venus would actually make you think left is right.
Right.
It's so frustrating.
Correct.
It's so frustrating. Oh, also, what if the planet's axis isn't, you know, perpendicular to the orbital plane like ours kind of is, right?
Yeah. What if you live on like Uranus, where
nailed it,
where it's like rotating because of some kind of ancient impact? It's rotating kind of with the North Pole, if you will, facing the sun.
Oh, you're so smart and so educated, and I love that you went right to Uranus because you are correct. Stop it! Don't laugh. No, but like Uranus, I should say, in the fun-killing way. Uranus is tilted at 98 degrees, right? Like the Earth is 23.5 degrees, and that's why we have like summer and winter like we do. Uranus is 98 degrees, which means it spends a quarter of its year, its orbit around the sun,
with Nick Lachey.
It spends a quarter of its year with one of the poles facing the sun, so it doesn't matter that it's rotating.
Right.
That side's in sunlight, and the other half is in darkness, and then, you know, it goes around the sun, and on the opposite side, the reverse is true, you know?
Yeah.
So it's just an absolute nightmare. And Uranus also has a quirky magnetic field. Like, our magnetic poles are close to the axes of rotation, right? But Uranus's magnetic pole is offset 60 degrees. So that's not helpful either.
Can't use that either. Jeez.
It's totally useless. So you might start to think like, what, do we have any common ground, pun kind of intended? And the answer is yes. We have to start thinking in terms of what is fundamentally true for us and for anything, anywhere in the universe. And the things that are true for that are the basics of mathematics, physics, chemistry. Basically, science can serve as a universal language.
So wait, are you about to tell me that I have to, in order to explain left and right, I have to figure out which direction an electron is going to orbit or something?
Oh, you're so on it. I hate how much that you know. But yes, basically, we'll get to that. We will get to that, right?
No. I love it.
I love this too, because this is something that, you know, we're not the first people to think of something like this, right? When scientists realized that we were starting to make probes that would leave the solar system, we might want to come up with ways to communicate. And then they ran into this problem of like, how do you do that?
Yeah. How do you communicate with somebody with no shared... I mean, we had trouble communicating here on Earth with people who grew up here on Earth and were evolved here on Earth, right? Mm-hmm. The reason the Rosetta Stone was a big deal was because we found the first time this like basis across different languages that had no basis together. You know, they weren't from a shared history. And so that's really hard to translate from. This is like a Rosetta Stone for another planet is not going to exist.
Mm-hmm, mm-hmm. But the great thing is, though, that people have put thought and time into considering how would we make a Rosetta Stone for another civilization, right?
Yeah.
And how could we make one that will survive a journey through space, whether it's a physical object or a radio signal?
Yeah.
So in 1960... there was a German mathematician. His name was Hans Freudenthal. He published a book titled Linkos, Design of a Language for Cosmic Intercourse.
Ooh.
I know.
Things in here are not sacred, you know what I'm saying?
I love that. It's like a guide on how to seduce aliens, which is clearly not... He means intercourse in like the conversational sense, not like the Captain Kirk sense.
Amazing.
But I do love that. And it's probably like a translation issue, which again shows such limitations of language, right? Like I'm sure the German word for intercourse means exactly like conversation, and then translated, it's like, ooh,
that's so funny.
Intercourse.
And all the English speakers are just like, like little teenage boys.
Whoa there, Hans. Okay, but being a mathematician, right, he says, hey, like mathematics is fundamentally the language of the universe, right? Like the symbols that might represent 1, 2, equals, multiply, whatever, those are all arbitrary, but the things they represent are not, right? Like one object, 2 objects, these are universal. And you can take that as a foundation, and then you can start with counting, and then expand to operations like addition, subtraction, multiplication. And you can keep building and building and building until you can establish a shared language based on mathematics, which is bananas.
Yeah. Huh.
So this book was pretty much not like utilized by anybody for a long time. I will get to later though, when it was kind of dusted off again.
Okay.
The first actual practical attempts to have some sort of communication, that started with Pioneers 10 and 11, these NASA probes. A few months before launch, actually, somebody approached Carl Sagan and said, hey, these 2 probes are actually going to have enough velocity to leave the solar system. What if we put a little message on there? And so Carl Sagan, along with Frank Drake, who was a professor at Cornell, and Sagan's wife at the time, Linda Salzman Sagan, they started designing this plaque. And you've probably seen it. It's fairly famous, but just in case you haven't, I will drop a link to it in the chat right here. And we can put that in our Instagram as well for listeners that want to actually see it.
Instagram is at That's Absurd Show. Also Threads and other places. Oh, yeah.
Nice.
Yeah. I've seen this.
Yeah. So go ahead and describe
it. It's like intergalactic porn. There's 2 naked people. And
that's where you go right away, huh?
Yeah, intercourse. That's where I'm going. It's intergalactic intercourse. That's what it is.
Intergalactic intercourse. Oh, no. Okay.
I get it, though. Okay, so yeah, I've seen this before.
Right. So this is a pretty well-known depiction. Voyager gets a lot of credit for the golden record, but Pioneers 10 and 11 were the first that were going to leave the solar system, even though they've been overtaken since then. And so we put this plaque on there. And when you start to analyze it, you can see a lot of the logic in what they were trying to communicate. So in the upper left, there are 2 atoms. They're supposed to represent hydrogen atoms, right? And the thinking was hydrogen is the most abundant element in the universe. Whoever we talk to who's going to find this, if they're going to be able to like locate a flying tiny object in space and grab it or whatever, they're probably going to be familiar with chemistry and familiar with hydrogen.
Right.
So the hydrogen atoms in the top left, they've got, the 1 proton in the middle and then the 1 electron, because hydrogen's dead simple as it gets for an element.
Right.
And the electron, you'll notice on the left, it's pointing down, and on the right, it's pointing up.
Yeah, why is that?
Well, that represents how the electron in hydrogen can change energy states, and the spin can change up and down. And when hydrogen changes energy states, it emits electromagnetic radiation, which is what's true when electrons generally change energy states. Like when light gets absorbed and then re-emitted by an object, that's the electrons absorbing it, changing states, and then changing back again and sending a photon off. So the electromagnetic wave that hydrogen gives off when it goes through this change is about 21 centimeters long. And the amount of time it takes to change between these 2 states is about 0.7 nanoseconds. And so that's going to be true here on Earth or on Mars or in another galaxy.
Got it.
So using that, we can start setting up a fundamental kind of metric for things. So in between those 2 hydrogen atoms, right, there's a little line.
Yeah.
And then there's a binary symbol for 1, right?
Yeah.
And so that's establishing like the distance of that wavelength, those 21 centimeters, that we're going to call just 1 unit.
Nice. So they were able to use this fundamental part of nature to create a whatever one is going to be for this plaque.
Exactly. A unit of distance as well as a unit of time. So when you look at those two drawings of the naked man and woman, the thought put into that was like, okay, you've got the guy waving, which is probably going to be meaningless to an alien civilization. But I think it's really interesting when you look at their postures, right? The man is more kind of upright and rigid, but the woman's posture is tilted over to one side and more relaxed. And the thinking was that shows, hey, our bodies are flexible. Like we can move, we're not just like stuck in a certain position.
You won't walk around. You won't see everyone on this planet with their arm
just with an arm
and
just standing there.
A nice 1960s or 70s comb haircut, just like standing there.
Yeah, exactly. But also, when you look to the right of the woman, you'll see there's little lines like denoting the top and bottom. And then between those lines, there's a binary number for 8. And that's going back to that 21 centimeter wavelength of the hydrogen atom emission and showing that, hey, we are typically about this tall, right? About 8 of these wavelengths, which in, freedom units, it's about 5'5", about a typical height for a human female. So then the other symbol on it, right? You've got that crazy kind of like explosion-y looking thing.
Yeah.
That's supposed to be a map to where our solar system is. It's tracing lines out to pulsars that we've discovered. And pulsars are these, rotating neutron stars that are shooting out energy. So they're kind of like giant cosmic lighthouses in space. So we figure they're probably visible to other civilizations. So if we tell you how far away they are, from us in all these different directions and tell you like which pulsars we're looking at with the little ticks and symbols on there that represent like the pulsar's period, like how often it sends out these signals, how many times per second. Right. You can actually triangulate where our solar system is relative to all that.
Which, if you're a big sci-fi nerd, a lot of sci-fi, when they get into like, especially harder sci-fi, when they get into how they're like, they've been teleported somewhere, right? It's always it's a trope in sci-fi, right? Oh, I was here, now I'm over here, and an alien did this, and we don't know how. And they're like, but we can't find ourselves in space. And that's, you can't use constellations. You use, typically what they're using is pulsars and like known pulsars. And so as we go out into space, these are very much like lighthouses that can show us where we are, where we are in our random location that this alien has dropped us. So if we see pulsars and we don't know any of them and we don't know any of their energy periods, then we're in a strange part of space, which is pretty cool. Yeah.
They can also show us when we are. Because pulsars, the signal degrades and, the period changes over time. So when we send this probe out into space, it's going to be traveling for a long, long, long time before anybody else probably ever finds it. If they find it,
right?
You can even figure out based on how these signals from the pulsars have changed and how much time has passed since this probe was sent out, which is pretty freaking cool.
That's pretty cool.
And then lastly, there's the actual image of our solar system. We show that we're, the third planet. This was back when we thought we had 9 planets. Sorry, Pluto. Again.
R.I.P.
And then the little arrow showing, the Voyager probe shape and how we shot it off from there. And the arrow, by the way, was a source of a lot of criticism because it was like, what if they don't understand what an arrow means?
I remember that. Yeah.
It's so hard to like recognize all the assumptions that you make whenever you try this kind of communication.
Yeah.
So that was Pioneers 10 and 11, which was pretty cool. In 1974, we actually sent a dedicated like radio blast out into space. This was again Frank Drake. Frank Drake is a prominent like member of SETI's Search for Extraterrestrial Intelligence Institute, and he's the guy behind the Drake equation that represents like the probability that there's intelligent life, in the galaxy or something. So pretty well-known guy. He devised this image that was encoded in binary, so you like bitmap it.
Oh, fun!
And he shot that out from the Arecibo radio telescope in Puerto Rico in 1974.
R.I.P.
Yeah, I know. RIP.
Damn it.
And it was aimed at a globular cluster of stars that's 21,000 light years away, so it won't get there for quite some time. Yeah. But anyway, I shared with you again the image, and we'll put it in our Instagram and elsewhere on social media. Trace, can you describe what that looks like?
Yeah, it's like, okay, firstly, it looks like an old school video game from like the 1990s. So it's just kind of 8-bit graphics. Actually, even worse, like Atari almost.
It's more like Atari 2600.
So simple. I'm going to start in the middle, even though that's not really the best place, because that's where my eye is drawn, because there's a little person, a little red person. And I can tell it's a person because I know what people look like. It's got a little head. It's got shoulders and arms and legs. But then around it, I don't even know. This looks like something from Commander Keen, or, one of those like games from the old IBM compatible. It's like some white pieces at the top, and then another little red thing that could be like a guy going, yeah, and then, but only the top half of it. And then a bunch of green things, which kind of look like the aliens from, what's that, from Missile Command or
Space
whatever.
Invaders.
Yeah, Space Invaders.
Yeah.
Yeah, that's it. And like, then there's like some waves, which I hope are waves. And then based on what we just learned, maybe there's a period here with like two little blue dashes and a little eye, another blue dash. And then there's another, what might be some kind of wavelength or something. Below that, it's just some different sized lines. And then below that is a big purple thing that looks like an M.
Yep. But, I mean, you described literally what's there. But what's actually, you want to know what it's supposed to be?
I'm sorry. It's very confusing.
Here's what it's supposed to be. It's supposed to be the Arecibo telescope itself.
Okay.
Our solar system, DNA, a stick figure of a human, you nailed that part, and then biochemicals of early life.
Oh. The green bits are the biochemicals?
I don't know. I stared at this thing for a long time, and I'm like, some of it, yeah, maybe, and others, I'm like, no idea. Don't feel bad, though, because Drake actually mailed, not even the image, he mailed the, binary actual message to a bunch of his friends, including like Nobel laureates, to see if they could decode it. Almost none of them had a freaking clue what to do with it. One person realized like, oh, it's a binary bitmap. And after that, like, still couldn't figure it out.
But so... okay, Drake, look, you are a very prominent and important person in our scientific world, but there are 4 different colors here. You could argue more because it's white, black, red, green, blue, and purple. Just decoding that, like, what does red mean? To us, it means something because our blood is red. We have these like connotations, but like you send it to an alien, red could mean like, I hate you. Red could be sacred to them, and you've besmirched it. Like, you have no idea what these colors mean.
I mean, again, assumptions. We got to go even deeper. We're assuming that they have eyes.
Yeah.
And that these eyes also see the same wavelengths that we see.
You're right. That's totally true. And we're assuming not only that they understand binary, but that they can decode it the way that we have encoded it, which I don't know if that's a universal. I'm not a computer scientist, so I wouldn't assume it's a universal way to encode anything, that it was a choice that we made based on how we invented computers and how we came to them. I don't know.
Well, binary, the advantage is it's mathematics, right? So, and it's base 2. So it's easy to send as a radio signal. It's like on is 1, off is 0. So like maybe you could figure it out that way, but then what the actual images themselves mean, probably not. And, the question says we've got a magic communicator, so we don't have to worry about aliens like not catching the message. But this thing took like less than 3 minutes to beam out. So if something wasn't there listening, pointed in our direction for these 3 minutes when this signal is going by, it's gonna blow right by them, and they're not gonna catch it.
That's it.
Right. Then we had Voyagers 1 and 2 in 1977. They had the gold records. The records also have, along with sounds of people greeting each other, it's also got sounds of dolphins and apes, because Julian, when Carl Sagan said, I want to make something with a lot of human greetings, she said, why just human? What if it's easier for them to interpret some other animal languages?
That's good. Break out of those assumptions.
Yeah, exactly. And then it's got 115 images encoded on it in like an analog format on this record. So you could possibly get, it's got Chuck Berry rock and roll. So that's nice. That's fun.
Yeah.
There's
that line from The West Wing where it talks about if it's ever found, there is the recording of Wet as the Night, Cold Was the Ground by blind Willie Johnson, who died penniless in his house that was burned down. And, it's just like we put a lot of human on this record.
Yeah, we really did. We did.
Dark was the night, cold was the ground. That's it. Yeah. It's a great song. Look it up.
I'm going to have to. I don't think I've heard it. I'm going to have to go and get me a copy of the Voyager record See if they sell it anywhere.
I'm sure they do. I'm sure they
At
do.
this point, it must be.
Yeah.
I'm sure. That would be, if you're a vinyl nerd, because vinyl nerds love being vinyl nerds, I think that's the ultimate like trump card.
Yeah.
You're like, wow, you've got an original pressing of the White Album? That's cool. I've got the Voyager record, the original. I went out and got it.
That's it.
Okay, I think the most productive, like most well thought out way of trying to establish some sort of language that we can communicate with extraterrestrials finally was thought out in 1999.
Oh.
So in around this time period, there was like a little crowdfunded effort called the Cosmic Call. And they were going to try and, first of all, the company behind it, which is based in Texas, was going to try and make a solar sail that would like fly out in 10,000 years, carry samples of like DNA and all this stuff to other extraterrestrial, extrasolar places. But before that, they're like, why don't we send a radio message? And they crowdsourced funding, and they said, hey, if you give us some funding, we'll put, an image of yours in the message, or some message, some audio, whatever, right? And so they're putting this together, and it gets the attention of a Canadian astrophysicist named Ivan Dudil. And Dudil goes, aliens aren't going to have a freaking clue what this means if you just blast this out there with nothing.
You're just blasting noise at them.
Just shooting gobbledygook, right? So he contacts the people behind it and says, hey, I'm an astrophysicist. Can I make like a preface to this call that you're going to send out? And they agree. He gets another Canadian physicist friend of his, Stéphane Dumas, involved. And they actually go and they check out that book of intercourse that we talked about earlier, that one from 1960. Yeah. They were the only people who had ever checked it out from their university library.
Oh, no.
They said it was the most boring book they'd ever read. It was also, by the way, the original title, it was part 1, and the author never wrote a part 2.
Oh, well,
so I think even he
checked it
kind
out
of
the library. So.
I think even he gave up on it, right? So they trudge through this, and they come up with their own kind of system of symbols that they could send out in binary on like a radio call. And they're really trying to make it resistant to noise, like other cosmic signals kind of interfering with what they're sending out. But they also designed it so when you actually put the bits of binary together, if you turn them into like 127, pieces of information by 127, it'd be like a page, a square page, and it would form these symbols, these glyphs. And the glyphs are designed so they can't be mirror imaged and be another glyph, and they can't be turned like the wrong way or anything. They're supposed to be like totally unique, and so they used it to start setting up on the first page like basic math. They have like a single dot, and then they have their symbol for equals, and then they have 4 binary digits to equal 1, and then they have the equal symbol again, and then they've come up with like a number 1 symbol, and they do this for like up to 20. And then they start on the next page defining like mathematical operations, multiplication, division, just like this German mathematician said, like, we can do this. And it starts to get more and more complex. They start representing like chemistry, chemical elements that they'd be familiar with. They start telling these aliens that might get this signal details about the Earth, like the composition of it based on these chemical elements.
Whoa.
And it just builds and builds and builds. By page 15
There's
of
15
27...
pages?
No. There are 23 pages of this. And by page 15, there's an image included that you might find familiar, which I will drop in the chat, and I'm sure we'll put on our social media.
Hey, it's our naked friends.
It's our naked friends again. But
she's
now,
smiling this time. It doesn't have a nose, weirdly.
Again, we're dealing with like binary digits.
Right.
So like there's only so much detail you can have, right?
That's cool.
And you can see her height now is represented, but using these numerical symbols that they've come up with. And then what I thought was really clever, if you look to the left of the man and woman, there's like dots that are falling, and that's supposed to represent the direction that gravity pulls on us towards the Earth. So you can tell like which way for us is like
would be
up or down.
Right.
Exactly.
I assume also, sorry to jump in there, I assume also that the gravitational acceleration is accurate. So it's...
I didn't find that, but I'm sure. Yeah.
If you looked at this, one would think you would be able to calculate on some level, maybe some approximate how our gravity must work and how much of gravity we have. I don't know. There's no time, so I'm not sure. But anyway, that's neat. That's really neat.
But you've got the right idea. You can start actually getting really complex. And then by the last page, there's just a bunch of questions. It's like, hey, tell us about yourself. What's your mass? What's your height? Like that sort of stuff using the symbols that they've established.
Cool.
So you could mathematically eventually get to a point to discuss all these things. And these two Canadian researchers actually spent months, figuring out how to do that with these symbols. And then they blasted it out. They picked 9 fairly nearby stars. It'll take 50 to 70 years for the signal to reach these stars. And they sent this code. The preface for the call is like a 4-hour long transmission, and they send it very slowly, like 100 bits per second, in order to make sure that the signal doesn't degrade. And then the actual call itself, with all the images that got crowdsourced and funded and stuff, is like way higher bit rate, so it's way more prone to degradation. And they sent the preface out multiple times so you could decode it, and then the actual call itself once, So the preface ended up being a lot more important.
It seems like.
But yeah, it shows that eventually you can get to this point where you can, assuming that they are advanced enough to have chemistry and mathematics, which if they're receiving this signal, they should be, you could get to a point, you have to make some assumptions about what they can do and can see in their senses and stuff, but eventually you could get to a point where you could discuss complex things, which leads us to particle physics and CPT symmetry that our anonymous asker's physics friend actually brought up. Basically, right, in particle physics, there's these laws of symmetry. Yeah. And we used to think that they were immutable, right? Like charge symmetry, parity symmetry, time symmetry. Like if you ran something in time in reverse, it should just happen in reverse like you'd expect, like rewinding a videotape.
Right.
The one we're going to focus on is the parity symmetry. And that's basically like a mirror image symmetry. The analogy I like is, imagine, okay, so we've got a clock, right? All the guts of the clock work so that when the clock is actually running, the hands tick clockwise around the face of the clock, right? Now, imagine you built the mirror image of this clock. You just took all the components and you built the mirror version of it, and when it's running, the clock should run counterclockwise, because everything inside is mirrored, right? So that's parity symmetry. So in 1956, physicists thought that all of these symmetries were immutable, that everything should apply, charge, parity, time reversal should all be symmetrical. And a physicist named Chien-Shiung Wu, she's Chinese American, in 1956, showed with an experiment that is not the case. She took a cobalt-60 atom, which has a spin. So, it's an analogy. It's not perfect, but you can think of it as like a spinning top. She polarized it magnetically, and then cobalt-60 is an isotope that decays. It undergoes beta decay. And when atoms go through beta decay, they spit out either an electron or a positively charged electron, a positron, right? These are beta decay particles. So when this cobalt atom was spinning and it decays, the electrons that it shoot out go in a certain direction. So Wu showed that even if you changed the direction of the spin, when it decayed, the beta decay particles still shoot out in the same direction they did when the spin was the other way. So that violates parity symmetry. Yeah. It shows the universe has a preference for which direction things go in, like left or right. And finally, it lets you definitively say that a certain direction is left or right, no matter what. You could communicate with these aliens and say, hey, check out a cobalt-60 isotope, observe the direction that stuff shoots off of it, and that is quote unquote left. Or whatever. Yeah. So my God. To answer this anonymous asker's question, you could define left or right.
Oh, God.
If you established a universal language based on mathematics and then both came to an understanding of particle physics and quantum physics and communicated that to them.
Wow. Oh my
And then they would
gosh.
know what left was. So suck it, Oxford Dictionary.
Yeah.
Suck it, Webster's. I like my definition better. Your left is what's more on the left is terrible.
I hate it when definitions define themselves using the word that they're trying to define.
The worst. The worst.
What
so
is
we've
big?
solved
Big
that.
are big things. Stop it. Wow. Cobalt 60. Who knew? Was there the whole time.
Thank you, Woo. I mean, I love the looking into this question was just like mind blowing upon mind blowing. Like, so cool.
I never wanted to be a woo girl before, but now I definitely do. But
big time woo heads over here.
I'm a woo head.
Big time fans of Woo.
Wow.
Amazing.
Jeez.
Whew.
I don't even have any questions. That was amazing. Thank you, Julian. And thank you, anonymous question asker. Let's take a quick break and everybody just like clear their head for a minute. And we'll come back with another question. Julian, give me your best dinosaur roar.
Oh, God, an asteroid! It's horrible!
Wow, that was not where I expected that to go. We're popping in before the show to tell you about I Know Dino. It's a dinosaur podcast.
You know, we think of those dinosaurs being this thing that's been dead for tens of millions of years. Even so, studying dinosaurs can still teach us stuff that is relevant to the world today.
Yeah, like climate models to help us understand global warming.
Migration patterns of dinosaur lineages, they tell us about Earth's changing continents.
We can also study dinosaur diets, what plants lived then, and maybe what animals and how they interact.
And, this is super cool, many dinosaur injuries, paleopathologies, they're the first known occurrences of diseases.
And they talk about all this kind of stuff on I Know Dino. It comes out every week with new dinosaur stories that you're not going to hear anywhere else. Like, I hadn't heard of a lot of these, which is pretty cool.
You can find I Know Dino on Apple Podcasts, Spotify, wherever podcasts are. And if you found us, you can probably find them. Go check them out. Welcome back to That's Absurd. Please elaborate. We are going to pick up where we left off with Trace's question from a listener. So, Trace, what did you dive into and answer for this episode?
Okay, I hope that your brains can take it, because the previous answer was a lot, but this one was, we thought both of these were going to be really simple, and then it turned out neither of them were simple. So 2024, bringing it hard.
For clarity, like, we're recording this during, like, right before our Christmas break, and Trace and I were like, I want to make sure that, like, we don't have to do anything over the holidays. Let's just take it easy. Let's pick some ones we'll just knock out real quick with a fun little record, and then it turned out to be this. But hey, you know who worked during her Christmas break? That was Woo. Woo did that experiment. So we can't complain. We cannot complain.
That's right.
She, like, literally changed particle physics on her break. We can answer a simple question or two.
That's right. So my question comes from Moma, and Moma asks, how would life have evolved if Earth was 2 or 3 times smaller?
Oh.
Yeah, really interesting.
I can tell you off the bat that's going to be complicated. I'm surprised that you were like, easy.
I thought it'd be really simple. So Moma goes on to say, a couple of times I thought about how weaker gravitational forces could have made a difference in technological advances of humans, but I always neglected the fact that a smaller planet would be such a strangely different place for life to evolve at all. And Moma, you nailed it right out of the gate for that. That is true. The world would be completely different. It's not the simple that I thought it was going to be. So basically, Moma wants to know, if Earth was half the size, how would that have changed how life evolved?
Question.
Yes.
Question. When we say half the size, like, in what actual metric is our size changing?
Yes. So the reason this was so hard for me is because of somewhat of the vagueness there, which it doesn't feel vague. Like, if you go to somebody and you're like, oh, if I had half the size of that bread loaf, what would that mean? And you're like, okay, cool, I'm going to split it in half. But when it comes to astrophysics, there are so many variables here. Like, half the size could mean just half the mass and the same volume. So less density. Half the size could mean literally you've got half the mass. mass that you had before, but how much space is that mass taking up? Half the size could mean the same amount of stuff, but it's squeezed into a smaller volume. Because there are so many variables, and I am not super confident in math, I spent probably 3 days trying to figure out all of this stuff. I recruited ChatGPT, which did not help at all. I asked an astrophysicist, but he was really busy because I don't know if you heard about space lasers, but he was working on that space laser thing with sending video.
Couldn't be bothered.
Oh, it was just like, wow. It was a lot.
So what you're saying is when the mathematical universal language from our alien friends, the reply comes back, you should not be manning the station that receives it and decodes it, is what I'm hearing.
Yes, that's true. I think we all know that from the way I described the 8-bit image. But hey, guys, he sent a little red fella with the purple dome.
It's Atari.
He said,
oh my God,
guys.
Oh, you got Space Invaders up there? Actually, that's a good question to ask them. Can you imagine the garbled... Do you have Space Invaders? And they're like, they're coming to invade us, and then they invade us.
So anyway, here's what I've got. Basically, I looked more closely at Moma's question, and they mentioned gravitational force at being weaker. So I was like, okay, so we know it's a weaker gravitational force. In order to have a weaker gravitational force, we have to have less mass. I mean, not entirely. There are other ways to have weaker gravitational forces, but we're not going to get into it. It's just way too much. So they also said if Earth was 2 to 3 times smaller. So we have a couple of constraints on our variables here. So Earth is a smaller size. I took that to mean a smaller volume. It's also 2 to 3 times. I picked 2 because it's easier for my brain. So I said half the radius. So if our volume is halved and thus our mass is equivalently reduced, what would happen to the planet? So first I had to figure that out.
Yeah, what I'm imagining, you ever go to like a science museum, which I hope people do regularly because they're so fun, but you ever see like the giant chairs that they have or whatever sometimes?
Yes.
And they're like, this chair, we scaled up all the dimensions by 3, but the mass is actually way bigger because things don't scale evenly like that.
Yes.
And then I'm just imagining factoring that into an equation to calculate gravity is just going to make everything a mess.
It's going to make everything a mess because gravity isn't as intuitive as we might feel like it is because we're under it all the time. So what I did is I looked up and found Newton's law of universal gravitation, which is little g, which is to say the gravitational force you're feeling, equals big G, which is the gravitational constant, universal throughout everything we know, times mass, and so it's big G times mass over the radius of the thing squared.
Okay. So the things that matter are the mass of the object that's pulling on you and radius from what? Center of the object?
Radius from the center of the object. Correct.
Okay. So the distance you are from the center. So the more massive it is, the more gravity you feel, but then the farther away it is, the less you feel.
Right. Exactly. Thank you for explaining that. That was great. So now Earth, our radius is 3,960 kilometers. And so then if we half that, we get to 1,980 kilometers, and we would have to have a name for that. So I was trying to come up with some. So I came up with Halfling Earth.
Cute.
Hobbit Earth.
Adorable.
But I think my favorite is Wee Earth.
Wee Earth.
It's just a wee Earth.
Just a wee little Earth.
We got a wee little Earth there. So we got Wee Earth, and we got Now Earth. So we need to find the mass of Wee Earth. So we're going to calculate the volume of a sphere, which is V equals 4/3 pi r cubed. I'm not going to go through all the math, but if you want to see it, just send us a message. I'll do my best. But basically, it comes out to Wee Earth is about 1/8 the size of Now Earth.
Sorry. In
volume.
Mass?
In volume.
In volume. Okay.
So the volume of the sphere ends up being reduced to 1/8 the size.
That is a wee Earth.
It's such a wee little Earth.
We'd live so much closer if that were the case. It'd be so nice.
It would be nice. And so now if we want to find the mass, and we assume the same density. So we're assuming that Earth has the same density as Wee Earth. So mass is volume times density. So again, works out to...
So it is 1/8. Yeah.
Also an eighth. Easy peasy. So Wee Earth is a 1/8 mass, 1/8 volume, sphere-ish thing.
Okay.
So anyway, let me just get to the thing that we need to know, which is little g equals big G times mass over the radius squared, the gravitational acceleration. And this is where I got really messed up and had to ask everybody for help because it's half. According to the math, it's exactly half.
Wait, it's just half?
It's half. So even though it's a 1/8 sized Wee Earth, in terms of its volume and 1/8 of
mass.
the mass of original Earth, it is somehow half.
Oh my God, I realized I probably could have gotten to that really quickly based on the formula you gave, right? Like big G times mass over radius squared. Well, if mass is 1/8 and radius is 1/2 squared, so 1/4, right? It would be like 1/8 times 4,
Yep.
which is 1/2. It is just 1/2.
It's just half. It's half.
That was a long walk.
It was a long walk to get
for
to
a very simple result.
roughly 4.9 meters per second squared.
That's the acceleration you feel.
The acceleration due to gravity.
Being pulled towards the Earth. So,
and I
so
thought,
half.
this cannot be right. And so I redid it several times. And like I said, I'm so just not confident in my math. But, so fun question. You want to reduce the mass of Earth, and you want half of the mass of Earth to go away. How much smaller is the Earth going to be?
Is it like negligible?
It's 20%. It's only 20% smaller.
That's not that bad.
No. So it's about 1/5 smaller, but it's still like mostly a big planet. Whereas if you want to reduce the mass, or if you want to reduce the radius, you're reducing it a ridiculous amount. So it's just like because of the way Moma asked the question, we ended up with this teeny little wee Earth. So that is a long way around to say you have a planet that is much smaller, about 1/8 the size, and it has about half of the gravitational pull that you're feeling at the surface. So we need to talk about it in a slightly different way than if you just went out and Googled this, which I appreciated from Moma, because most of the people, when you just go Google these things, they say if we shrunk Earth, which is to say we either compressed it or we cut it in half or we do something to it. And in doing that, we're changing a planet that already has life on it. And Moma is asking, what if it formed that way? How would life have evolved, right? And that's where we end up with our problem of trying to answer this question. Because one, there is no way to know, right? There's just no real way to know exactly what this random planet would have had happen. However, let's talk a little bit about planetary formation. So just to give you a little background. Julian, can you tell me how planets form? Please answer in the form of a haiku.
Oh, God. Okay.
I've got one. But
hold on. No. I'm going to try. Dust gathers disc-like, forms by accretion to balls, sphere shapes take over. I think for an impromptu haiku, an impromptu coup, that is not bad.
That was pretty good. So here's what I got. I have...
By the way, I hate you for throwing that at me out of the blue.
You're welcome.
Thank you for that. Okay, so did you write this or did you find this?
No, I made this up.
Nice.
Here's what I got. Accretion disk spins, coalescing gas and dust, forming a planet.
Wow.
Thank you.
We had a lot of overlap there.
A lot of overlap. I was really happy to hear the overlap.
Yeah, the teacher would definitely check our homework and be like, I think they might have copied each other or something. Love the word accretion. Great word. Solid vocab word.
It is great. And it has a lot of syllables, which is fun for a haiku. Try and fit it in.
That's what I was thinking. Like that's why I saved it for this. That's why I saved it for the 7 line.
That's where I added coalescing. I was like,
ooh. What is it? Haikus are pretty, but they don't always make sense. Refrigerator.
Yes. Okay, so planets form by essentially you have this big disk that will become a solar system, and stuff falls into the middle of it to make the star, and then the stuff floating around the outside that doesn't fall into the middle can form into planets. So to keep it simple and to save everybody's brains from this point on, we're not going to do any more math. We're just going to remind you that the planet is roughly a 1/8 sized planet in terms of its volume, and it's got half the gravity. Deal?
Okay.
Great.
Deal.
Great.
I love it.
So we're just plain smaller. What would that change about the planet that we're living on? Firstly, Earth's core, right? Earth is smaller, and so its little core is little. It's even weirder.
It's wee
little tiny Earth.
Well, that's spinning iron car.
So most small planets don't have particularly strong magnetic fields, which are quite important for life. Earth now has a pretty good magnetic field. It protects us. That charged particle field protects us from solar wind. So the magnetic field of the wee Earth would be also smaller or non-existent. We have a magnetic field now because there's this iron core in Earth swirling around. Why is it swirling? Because Earth is hot on the inside. And so it's cooling off and it's rotating, and all of that ends up creating this dynamo that builds the magnetic field around us. Without those charged particles, the surface of the Earth is going to look more like Mars than it does like what we have now. So whether or not this wee Earth has a powerful enough magnetic field is tough to say, right? We don't know. There's no way to know that. But let's assume somehow that we still have one. Mercury's is only 1% of our strength magnetic field. Mars doesn't have one. Half radius wee Earth, let's say, has one, just to give life a fighting chance. Wee Earth also has another change, 1/4 the surface area based on my math. So less surface area means that the horizon is closer. Wee Earth is about 1/4 of the surface area of now Earth, or about 120 million square kilometers, which means, it doesn't really change much, but it's kind of neat to say like, oh, well, you can't see as far. Standing on at sea level, you wouldn't be able to see as far into the distance before things started to drop below the horizon, which is kind of cool.
That's cool.
Because the wee Earth is curving away from you more quickly than you would. Not a huge change, but it's kind of fun to think about. While standing at sea level also, the atmospheric pressure is going to be half, because atmospheric pressure is based on our gravity. So an easy way to think of atmospheric pressure is the weight of the air between you and space. So it's all of that air pushing down on you right now. Something
pushing down on me. No one asked for.
Yes, exactly.
Sorry, had to.
So we'd have half that pressure, which just means a lot less atmosphere above us. So wee Earth can't hold the air as close to itself as now Earth can. So because of that, we have just less air around. And less air has a lot of effects. Like, this is a pretty lower air. This would be the equivalent of us living at 5,500 meters, or about 18,000 feet up in our current atmosphere. That's quite high up. There's not a lot of atmosphere. It's 50% less air than we have now. So that means a lower boiling point for all fluids. So like water would boil at 20% less temperature than it does now, or about 80 Celsius, or around 200, a little less than 200 Fahrenheit. There's less water vapor in the air just because there's less air. There's less oxygen in the air because, again, there's just less air. I mean, that's not super ideal for life. That said, life did evolve without oxygen. So oxygen itself is not the only thing we need. We need other stuff too. It was in water, but that water was being warmed by volcanic activity in a lot of cases, right? We were keeping the water warm to keep it ideal for life. So not having a super strong atmosphere is not a deal breaker, but again, it makes things a little more complicated. Especially because larger planets cool more slowly than smaller planets. So like Mars might have some Mars quakes. We've detected them. We know they're there, but it's not the same as Earth. Like, Earth is tectonically very active relatively to Mars. Mars is cooler than Earth on the inside of its planet. Mercury has also cooled. Venus and Earth, they have not yet. So they have tectonic activity. We think Mars used to maybe have life because it used to have this internal heat that was reshaping the crust and bringing all this heat to the surface of the planet. Right now you find a lot of really cool life near vents under the oceans in Earth, and that's likely where our life came from. But if you have a smaller planet, it cools a lot sooner. And so we might not have seen as much life be able to come up, which is interesting. And now, of course, we have volcanoes that create fertile soil and, lots of minerals and things like that, kind of churning that crust to give us a little more chance for life to catch on.
Yeah, just recycling. Yeah, and bringing new stuff up. But yeah.
So we've got this cold, wee Earth that doesn't have as much air. It doesn't have as much water available to life. It's not as warm. It just might not be around for long enough to let life form. But then we've also got that half gravity, and that's really wild as well. So less gravity means less gravitation both on the surface, but also around the planet, right? How do you typically describe gravity when you want to get complicated, but not too complicated?
the classic analogy, right, is the like surface of a trampoline.
Yeah.
And then like something heavy kind of caused that dip in the surface, and so things like roll towards the dip. Right, it's like a 2D visualization of a 3D bending of space.
Yeah,
basically, is what I always imagine.
I think that's a really good one. I use those things where you put a penny and they were like the mall or the arcade or whatever, and it just like swirls around until it gets near the middle, and then it drops into the bottom to donate to kids with cancers or whatever hospitals nearby. That's another. It's basically we just described the same idea. It's this kind of slow curvature with something in the middle. And so right now, if you think of Earth being one of those, a trampoline, right now we've got a smaller trampoline. We don't have as much influence around the actual planet. It can't affect as big an area. This turns out to be really big deal as far as I can tell, because Earth got its water, we think, from comets and other things that flew by. If we have less gravity, would we have less water? Would we have less stuff on the planet? The gravity of Earth can't pull things from as far away as a gravity of a bigger Earth. So, which I think is just so interesting to ponder. Yeah.
So these comets, though, I mean, they're orbiting the sun, right?
Yes.
And they're heating up as they're approaching the sun, and they're melting and leaving like that water in their trail or whatever. And then I guess the thinking is like when we sweep through that trail, we're like scooping up some of that water.
I think that's
on
part
Earth
of it
for ourselves.
I think some of it too is when we were kind of a protoplanet still, and there was just a lot more stuff in the solar system. Stuff hit us more.
Oh yeah,
just like we were just getting hit by stuff because there was just more junk out in the solar system. And so there's these comets of like dust and rocks and ice, and we're using our gravity. We're not using it, it's happening, it just exists. So they're getting caught in our gravity as they're orbiting the sun and just happen to fall onto our planet and deposit their water and their minerals here. And if we have less gravity, we just have less opportunity to pull them in. They might get pulled in by Jupiter or one of the other planets.
Jupiter pilfering our water, that jerk.
Jupiter. But
actually probably saved us from a lot of impacts with the big old gravity. Thanks, Jupiter.
Thanks, Jupiter.
I take it back. Thanks, Jupiter.
But I like to think that maybe because we are so much less, we have just half the gravity, we may not have pulled in Thea. And that is a huge one.
The object that smacked into us and resulted in our moon, we think, right? We did that on a previous episode.
That's right. So
our episode with Ali Mateau.
That's right. So Thea is this is what they call this object they think hit us, which ended up forming the moon and like re-liquefying our crust with the huge impact that it caused. So without enough gravity to pull Thea toward us, what if we didn't? What if we just didn't have enough gravity to capture it, and it was captured by a different planet, or just ended up, in the asteroid belt? Or I don't know enough about the early solar system. I'm just postulating all sorts of things here based on what we know. But no moon means severely reduced tides. It means a different weather system. It also means, Julian, you mentioned the tilt of the Earth, and so Thea our moon helped stabilize that tilt. So we would tilt as much as 45 degrees. And now we only are tilting like about 23 or so. And that tilting is what moderates our weather, so it's pretty predictable. Without that, our weather could be much crazier. We'd have different, like our winters would be really harsh and our summers could be really hot. And it just could change all sorts of things, including the length of the day, because if we don't get hit by Thea, we might not slow down as much.
We were spinning a lot faster, early days before our moon started forming and like pulling on us, right? And like kind of tugging on the rotation of the Earth and slowing us down.
Yeah.
Because it creates like a bulge, right? And then it pulls on that bulge a little bit.
Yeah.
Oh, man. So we'd be on possibly like a much faster spinning, more barren,
colder,
but low gravity,
less
colder
air,
rock.
Maybe as much water, but probably less water. And it's really interesting to think about whether life could form at all on a planet like that, right? If we have a smaller planet is likely going to have a different day-night cycle. There's really no calculation for what a day-night cycle is going to be. There's not like, a planet of this size has a day-night cycle of that. Like there's no rule for that. And in fact, when I was looking this up, they're like, well, the best way to know what a day-night cycle would be for a planet is to watch it. And like watch it 1,000 times and see how long it takes to get back to where it started. And
like a year, we can know how long a year is predictably from like distance to the sun, but day, totally different ballgame.
Because they're all completely different. So Thea's impact changed it, but also there's just not a direct, it's called the sidereal day. There's not like a good calculation for that. Every planet is sort of different in those ways.
Is that how it's pronounced? I've been saying sidereal day my whole life.
So I started doing this PBS Stargazers show a few years ago, and so now I have to talk about astronomy, and so I had to look it up, and it is sidereal. I got corrected on the show once.
Oh my gosh.
Because I also called it sidereal, because that's what it is. It's the word side and real, and they smush them together. But it's sidereal. Yeah.
Oh, good to know.
So if it let's kind of go both ways really quick. If the day were slower and we had a longer day, that would affect how much atmospheric heating different parts of the planet are going to get, right? If the day is slower, the sun is shining on places for longer. Whether that's going to be good or bad, don't know. If there's less atmosphere, maybe it's good. We end up with some places that are getting heated enough in order to grow plant life. If it's, maybe not good, then we end up with something more barren. And again, this is dependent on whether there's a magnetic field to stop all of those charged particles from shooting onto that one place for longer. If there were longer, shorter days, there's less heating, which might mean a colder planet, but it's just so hard to say. So even if life did form and got past its microbial phases and through some kind of great oxygenation event, which it would have to either go on for longer or work harder to make enough oxygen to get to plant life the way we have now, it would just get really messy to even think about how to make life like us. And Moma mentions, I wonder how human technology would be affected by this. And it's like, are we even going to have humans?
That's what I'm assuming. The funny thing, I think there's very common kind of misunderstanding of evolution and whatnot, that a lot of people who don't understand it as well tend to disregard it because they're like, well, how come we're so perfectly suited? The Earth is so perfectly suited for us. And it's like, no.
It's the entirely
it's
opposite,
the other way around.
Yeah.
Right?
We are not Thanos. We are not inevitable.
Yes, exactly. Whatever life does form and take shape or whatever is gonna have to work in the environment that it's given.
Yes.
And so, who knows what that looks like? I love programs that talk about what could life on a gas giant look like, and it's maybe they're giant floating balloon organisms, who knows?
There's no way to know. I think you'll appreciate this too. The Coriolis effect would be different.
Oh, yeah?
Yeah, because the way the Coriolis effect works now, if you don't know what it is, it's like...
Of course I know what it is, but why don't you remind me? Why don't you remind everybody listening?
Yeah, the rotation of the planet, the atmosphere rotates differently, right? Because the ground is what's rotating and the atmosphere is being essentially pulled along as it falls into the planet because of gravity. The gravity's sort of holding on to it, but it's kind of behind the planet, if you will. As it's rotating, it's throwing the air around, causing all of these different swirls and turbulent flow. There's a really good YouTube video about it. I think Derek from Veritasium made it. It's really great. So Coriolis effect is cool because the ground at the equator is moving really fast and the poles are moving really slow. And in fact, if you're standing on the Earth's pole, you're essentially turning super duper slow. But if you're on the equator, you're booking it around the planet.
Right.
And on a smaller planet, a planet that's 1/8 the volume, has less radius, it's just a smaller planet, the Coriolis effect is lessened.
That makes sense.
That, I think, is really neat, which might mean more powerful cyclones in some places, but it also could mean just less weather. In general, just less weather. And with no moon, even less weather and less tides and less everything. So it just really hammers home that life doesn't just happen. We have all of these really complicated things that exist that allowed us to not just have life happen, but that it was stable enough that life could continue for long enough to get to us. There are things, though, that wouldn't change, which I think was interesting. Kepler found in orbital mechanics that planetary mass does not affect orbital period around the star.
Nope.
Which is cool.
Yep.
So the year would be the same, which is
cool.
Nice.
Good news.
Yeah, kind of cool.
Don't have to relearn that.
Yeah, you don't have to relearn it, but you might have more days or fewer days in that year. But yeah, I love the positivity that all of this would lead to us happening and just exist without all of these stabilizations, we essentially have all of these crutches, the moon, the size of our planet, all of those things have happened. And we are just so darn lucky that they all did, because it's stable enough for us to exist.
Yeah. I don't know, Trace. I feel like if, the dominant life form on We Earth was like basically Jello, like sentient Jello, and sentient Jello Trace and sentient Jello Julian, I think we'd still find each other and make a blobcast.
Like a cube, like a cube of Jello, like
Dungeons and
like
Dragons. A gelatinous cube.
Yeah.
That moves perfectly in your 6x6 hallway or whatever. Yeah,
exactly. So that's funny because I was trying to wrap this up, and here's what I wrote. I think you're gonna like this, and it's funny that our brains worked a similar way. I wrote, less atmospheric pressure means that there's less lift from pushing on the air, so there's probably no flying animals, which means dragons are still fiction. However, if you did have an animal that could generate its own heat internally, that might be beneficial. But if there were bipedal human-style things they would be smaller in stature.
Oh my
more
God.
Efficient at processing oxygen. You seem upset.
I already know where this is going.
They would have more body hair to stay warm, and of course would probably want to hang out in warmer, more cozy parts of the world. Maybe near volcanic activity.
Like a Middle Earth kind of part
like
of the
a Middle
world?
Earth. Maybe they would have nice heavy articles of clothing, and maybe drink alcohol to open up their blood vessels, and perhaps. Maybe some of their friends would delve greedily and deep into the underground where it's warmer. Just We Earth. It would just have little hobbits, little dwarfs.
Well,
just
and it's
running around.
I realized that's where when you started with Hobbit Earth, I'm like, he's coming back to Hobbit Earth, isn't he? He's coming back. And for all the fantasy nerds, I know that middle means like middle time period of Earth, not like this more
not the middle of Earth.
Come on, don't come at me.
I did look it up though, and the surface area of Middle Earth is supposed to be like 1 point something million kilometers, and the surface area of We Earth being 120 something, I was like, well, darn it, I can't get it exact, but that's fine.
It can't all be perfect. Look, Tolkien was more of a linguist. He wasn't like a physicist.
That's right. So anyway, to answer Moma's question, how would life have evolved if Earth was 2 to 3 times smaller? I don't think it would have. I honestly think there are just too many barriers. But if it did evolve, it would be so radically different from us.
As to be unimaginable.
It's just, however, whatever fantasy you can come up with, that is just as likely almost as almost any other. It's just, we just have no concept of what that would look like.
I mean, even given Earth as it, did exist, the directions that things go, it's all just like my favorite description, right? It's like non-random selection of random mutations, right? So like you've got that period of time where the dominant life forms that spread across the world, right, are like these reptiles with special hips and feathers, and then like you hit a hard reset and fast forward millions of years, and like the life on Earth looks completely different. Like you don't even have to change anything. It's like if you just started again from scratch the exact same way, like who knows what's here instead of us and everything we see.
That's right.
Which I think is a cool thing to think about.
I think it is super cool. Yeah, that is I like that you mentioned there was a reset. That's something else that I didn't put in here, but it's like a lot of our great extinctions have come from stuff hitting us, and maybe they wouldn't have hit us, which means there wouldn't be resets, which again makes it even less likely that mammals and then us would have come about, because whomever showed up first, post great oxygenation and the extinctions that are caused by us. Now, but... Or
like, you mentioned that plate tectonics might slow down and stop much earlier. And some of the extinctions we think might be caused by like these new continents forming and like the flow of currents and weather changing so much. Like it is such a massive variable that you introduce so early in this equation that leads to like the present day that, the butterfly effect, the differences down the road are just unfathomable.
Astronomical.
You
it's
cannot
just, you never know.
picture how different it would be, which is kind of, I feel like, a cop-out answer for the show, but I think it's true.
This is why this one was so hard. I wanted to give Moma a satisfying answer of like, well, people would look like this, or, we would do that, and it was just, it wasn't coming together. And I think a big part of that is just, there's no way for us to know, and there's no way that we are inevitable. So, man.
I think it's why the shrinking answer is so much more prevalent, because you could say, okay, if we take everything now and reduced it down, then what happens? And that's easier to fathom. But the we start smaller question, is like...
Right. The formation means that we'll just... If you start at a different thing than what we are now, in any capacity, there may not be an us.
Yeah.
Wow.
There's almost definitely not an us.
What a great way to start 2024. We're almost not going to be.
Hey, be happy you're here. How about that?
Yeah,
it's been a rough couple of years. Any number of things could have meant that wasn't the case.
That's right.
And so the fact that you're here is like a statistical improbability, and just grab it and run with it. Just be so glad it's you here now getting to experience it.
Right here, right now. Watching the world wake up from history.
Is that a reference to something?
It's a music song. It's a music song.
Good music. Now that's what I call music.
Yeah. Now that's what I call We Earth.
Well, thank you, Trace.
You're very welcome. Thank you, Moma, for asking that question. And thanks to you for listening to this episode of That's Absurd, Please Elaborate. We'll be back in 2 weeks with another episode. This show was created, written, and produced by me, Trace Dominguez.
And me, Julian Huguet.
It was also produced and edited by the wonderful and wonderfully talented Kyle Sisk.
A special thanks to the listeners who submitted questions featured in this episode. We had one anonymous listener and Moma. If you yourself come up with a question you'd like to ask us, please don't be shy. We've got a form for you to fill out in the show notes, or you can email us at hello@that'sabsurdshow.com. We've even got a website, that'sabsurdshow.com/ask. These questions are the lifeblood of the show. They give us so much joy. They're so fun to tackle. And frankly, we just couldn't have nearly as much creativity as all of you seem to have all the time. So please, keep those questions coming. We really appreciate it, and it's what makes the show go.
And finally, a very special thanks to those of you who listen on Nebula. Thank you also for writing in that you listen on Nebula when you ask a question. Nebula is a streaming service where you can support creators. You can get ad-free versions of the episodes and even support other independent creators and listen to our show without ads. All you have to do is join with our link, and you can support the show directly that way. Nebula.tv/that'sabsurdshow is the link. You can find it in the show notes as well.
We'll see you for the next episode. In the meantime, remember, reminder to come up with a catchphrase before we record.
What a good phrase. I love it. You said it, buddy. It's so stupid.